dollars.
They're expensive to build,
Yes.
and because they're unique, we expect it to be quite expensive.
Yeah,
But
that's
the
almost
actual
like a
prices,
I mean, it's prototype type cost. I mean, it's certainly not the point of mass manufacturing. There's no economies of scale coming in here, right? Right.
there are economies of scale, but they go the other way. It's not large scale; it's small scale.
Each
Yeah,
bit,
no,
okay, yeah.
absolutely. When we're able to build a machine that can clearly smoke its competition, um, we're going to make sure everybody knows about it.
Are you going to be able to smoke them this year before the end of 2008?
It's possible, but it's not guaranteed. I think that one of the things you said earlier is wrong. You can't do this sort of thing with only a few hundred bits and expect to beat the best classical stuff out there. You probably need at least 1,000 and maybe more.
Oh, okay.
So the expectation we've got is when we can put 1,000 or 2,000 qubits on a chip and get the algorithms part right, we stand a chance of beating a conventional system of the same
I understand.
price.
Yes, I understand now. Earlier this year, when you had talked about it, you thought that possibly I was under the understanding that 100 or 200 qubits could allow you to run a program, time it, and then be able to say, "Look at this. We've completed this search or matching algorithm or the traveling sales program in 2 picoseconds, which is infinitely faster than any class can be."
Well, we won't be able to do it in 2 picoseconds.
Okay. I'm just making up numbers here. Okay, I'm just making up numbers.
So there is something you can do with a smaller number of bits, and that's to verify that the way that the algorithm scales is in accordance with your expectations for quantum algorithms. So the whole idea of quantum computing is that as you increase the size of the problem, the computational resources consumed, like time, only grow relatively slowly compared to the classical approaches. So, for example, you could solve a problem with 50 bits, and then 60, and then 70, and then 80, and then 90, time all of those, and you can see a pattern emerge which shows you how much harder the problem is getting as you increase the size of the problem. Those sorts of things are very interesting from the point of view of showing that the machine is a quantum computer.
Okay.
And you can do those things with less bits. But you won't be able to use that type of machine to compete directly in terms of performance with the conventional approaches, because computers today are very, very good at what they do.
Yeah, I suppose you've got input output type things that take time as well. I suppose
that's true.
Okay.
Yep.
So there's a chance. Let's say there's a chance that you will be having an announcement before the end of this year. You'll at least
there is a chance, yeah.
Okay.
And that announcement will be a big one. It'll be the sort of thing where a new type of computer that can do something that no other computer can do is now available for purchase. That will be the kind of announcement.
Okay. Well, I certainly wish you luck, because I am very excited to see quantum computers come along, because I do think they will have quite a wide range of applications, more than perhaps we even think of now.
That's absolutely true.
Once people get a hold of them and start using them, just like any technology.
Absolutely.
Right. So I'm very happy. I wish you the best of luck. Sad to hear that we don't have a big announcement yet in 2008, but perhaps by the end of the year. Okay. Audience member did have a question about the size of the machines. Someone apparently said that one of your machines is the size of a supercomputer farm. One of these big, like Blue Gene L, takes up an entire room. Do you anticipate, as you scale up to 1,000 qubits, 10,000 qubits, will you be miniaturizing things? Is that something that you're working on at this point? Or is it just that it's such in a prototype stage that you just keep adding the components as they currently exist, the size?
So the machine right now is actually not all that large.
It isn't.
It takes up the size of a small room, sort of 10 by 10.
A 10 by 10 room. Okay.
Yeah. Its main size component is a refrigerator unit that's roughly the size of a kitchen fridge.
Yeah, I think I have a picture of that. Yeah.
Yeah. So if you think about it, like what it would look like in an actual deployed unit that you'd install in somebody's location, it will look a lot like the early Cray machines. It'll be fairly big, but it won't be tennis court size. We're talking about something that's maybe 2 kitchen fridges side by side. As you scale those machines up, we don't expect that they're going to get bigger. We expect they're going to get smaller. The main thing that changes as you go to larger numbers of qubits is the chip gets a little bigger because you need to accommodate all of the devices. But the infrastructure that the chip surrounds the chip, the sample holder, the wiring, and all that stuff, is going to be roughly the same size. So you could imagine fitting, 100 million qubits quantum computer is going to be roughly the same size as the ones that we're operating now.
Oh, okay.
And it actually might be quite a bit smaller. It's entirely possible that you could put a dilution refrigerator, which is the size of the main component now, and shrink it down to the size of a tower, like a workstation tower. I don't think there's any reason why you couldn't do that.
Oh, okay.
So, at some point in the future, it's possible that you could have units that are roughly the size of today's PCs that have, million or 100 million qubit quantum computers in them. I don't think that that's totally infeasible.
Okay.
It's certainly not within reach today, and it's not something you ever plan to do, but looking forward, I don't see any fundamental reason why you couldn't.
Okay. Yeah, and I was just wanted to again explain that your quantum computer right now is in what's called a dilution fridge or refrigeration, where you cool it with liquid helium, correct?
That's correct.
And the actual machine it operates at a temperature of 4 degrees above absolute zero?
No, it's a lot colder than that.
Oh, it is. Oh, it's only millikelvins. Yeah. Is that it?
About 10 millikelvin is about the temperature that the chip is at when it's operating.
Okay.
So just to give you a sense of the scale, it's about 500 times colder than interstellar space.
Right.
So it's very, very cold. And the part of the machine that's cold is a block of copper that weighs about 5 pounds. So there's roughly 5 pounds of copper, which includes the sample holder, which isn't made of copper, but it's attached to a copper block, and the processor itself. So the entire volume of cooling is about the size of like an instant coffee can.
Okay.
And the rest of the machine is at various stages of temperature, but only that part is as cold as 10 millikelvin.
10 millikelvin, I see. Okay, and another thing I wanted to ask about then, we'll move on a little bit to discussing about longevity, since that's what, at the Institute, that's what we focus on quite a bit. And I just want to ask your opinion on if you see any immediate applications for quantum computer such as yours that would be applicable to aging research. Anything that comes off the top of your head?
Well, I have a very strong interest in this field, but I come at it from a little bit of a different perspective. So I over the last few years have had an intense interest in artificial intelligence. And
okay.
I actually don't like that term, but what's
your preferred term?
Well, I'm not sure, but something like machine sentience.
Okay.
I'm not. It's not one of the. I'm not one of these people who wants to make computers human. What I'd like to be able to do is give computers the ability to reason and interact with their environments in ways that we think of as typically human, but will ultimately be much better than that. Okay. So, computers are much better than people at lots of things. And we kind of have given them that territory without it hurting our egos too much,
right.
Like multiplying and things like that.
Right.
But I think ultimately computers can be better than humans at everything.
I agree with you there, yeah.
So what I want to be able to understand is how to make that happen. So one of the areas that we're working in right now is applying our machines to a canonical hard intelligence problem, which is object detection in images. So imagine you have an image and you want to, and it's just an image, and you want to tag it with words that associate the things in the image to some concept, like a tree or a car or something like that. So we're working now with some scientists at Google to figure out how to map that problem into our hardware. So in the short term, what I'm extremely interested in is taking hard artificial intelligence problems that have no good solutions today on conventional computers and writing applications that use our hardware to solve them and seeing how they do. So things like vision, speech recognition,